Okay, welcome back to lecture, let's call it 9.3, where we're going to continue our discussion of Everest, but talk about the adiabatic lapse rate. Okay, so what do I... last time we've broken this Everest scenario up into three chunks. The first one where we assumed a uniform density. The second one where we assumed a non-uniform density, but that the process was isothermal, that the temperature didn't vary across the atmosphere. And that actually got us very close to the correct answer, right? We had this exponential dependence on pressure or on density. Now, the big question is, we know that the temperature profile of the atmosphere is non-uniform, right? We know that it's not isothermal. We know that if you were to as you go up in altitude, things get colder, right? Often we've probably taken a plane and you've seen the water, turning into ice crystals on the outside of the plane. Or you can just see the snow on the top of a mountain, right? Go to Banff or Jasper and you can see that's why glaciers remain at the top of mountains, right? But not at sea level. Okay, so how do we account for this, right? How do we account for the fact that the air is colder as we go up? Well, the way to think about it, you can tell I really should have gone to art school. Here's my Everest, right? So here's the sun. And let's think about what happens. So most of the Earth isn't, for example, a mountain. So most of the Earth, the solar radiation comes down and hits the Earth, right? What does it do? It's absorbed. Never know if I know spell that word right. And heat up, right? The surface of the Earth is going to heat up from the solar radiation. We've all been outside, and we know that it's hotter in the sun than it is in the shade. Okay? So we know that we can absorb that heat. All right, so that's better. Look at that. All right, so now if this is going to heat the air near the Earth, right? Now what happens? Well, the hot air is less dense than cold air, right? So now that this air is hot and it starts to expand, right? It starts to, well, you don't know that it expands yet. We know that it's less dense, and so we know that less dense means more buoyant, right? So the less dense air will rise. Okay? Now, we know, though, that as the air rises, the pressure drops. We did that last time, right? So when the pressure drops, we're going to get an expansion process. So our air is going to undergo an expansion. Okay, we've been thinking lots about expansion. So what kind of expansion process is it? Is it going to be isochoric, isobaric, isothermal, or adiabatic expansion? Okay, so isochoric, of course not, because that means constant volume, so that's not a right one. Is it isobaric? Well, no, we just told you that the process happens because the pressure drops. Is it isothermal? Well, no, we just said that, we know that it's going to get colder as we get up. So is it adiabatic expansion? And the answer is yes. It's almost adiabatic expansion. That is, as the air rises and expands, it really isn't exchanging heat with its surroundings. First off, it's doing this very quickly, and so there's not even enough time for it to exchange. And also the cross-section of the air with the surroundings is very small, right? So there's very little time or opportunity for the air to exchange heat, and so therefore it's basically adiabatic. Okay? So we're going to do now the adiabatic expansion of the atmosphere. So, adiabatic expansion. What do we know? So, okay, so first off, we had adiabats. We described them in terms of pressure, temperature, and volume, right? Now we can pick any two of them to describe this adiabat. So which ones are the ones we're going to think about? Well, I think volume's a bad choice, right? I think we should think in temperature and pressure. And so we're going to write down our temperature, pressure, adiabat equation. T to the gamma, P to the 1 minus gamma equals a constant along an adiabat. Okay, so we know that constant actually can be our T0, P0, right? Where our temperature and pressure were at sea level. So that's going to be great. We're going to basically assume 300 and atmospheric and sea level. Okay, so now we just need to know what is gamma for air? So, what is gamma? Remember, gamma was CP over CV, which was CP plus CV plus NR over CV. Okay, so what was CV for an ideal gas? So it depends on if it was diatomic or monatomic, right? So this is air, so we're going to assume that it's N2, right? It's mostly N2. So we're going to need to have a diatomic, right? So CV was 5/2 NR plus NR over 5/2 NR plus NR. So that's going to be 5/2 plus 2/2, so that's 7/2 over 5/2, so that's 7/5, right? So we've done that a lot of times now. We know that that's 7/5. Okay, so for Everest, what's the temperature? Well, last time we calculated the pressure. We calculated the pressure on Everest to be 36.5 kilopascals. So now we can calculate the temperature on the top of Everest. Okay, so we're going to say that the temperature, the gamma, is going to be at the temperature at sea level. We're going to call that 300. So 300 to the gamma is going to be P0, 1. So let's call it 101.3 over 36.5 to the. Let's actually put in. This should be, I think we can leave that out. Call this 1 minus gamma over gamma, right? I take the gamma root of both sides. So this should be 300 times 2.78. So this is 1 minus 7/5. So this is going to be 1 minus 7/5 over 7/5. Right? So that's going to be 5/5. So that's minus 2/5. So this is minus 2/7. So minus 2/7. Type that into your calculator, and you get 224 Kelvin. Woohoo! So that means we had an approximately 76 Kelvin drop, or equivalently, remember delta T for Kelvin and delta T for Celsius is identical. So this means it's a 76 degrees Celsius drop from sea level. Right? Or if this was 27, right, at sea level, which is a hot day, but it was 31 here today, so that's totally reasonable. So 27, let's see, 27, let's call it 26, so minus 76, that's minus 50. That's approximately minus 50 degrees Celsius. That's cold. That is even colder than Edmonton in January. Okay. So now we have the tools to define something called the adiabatic lapse rate. So the adiabatic lapse rate is the rate at which temperature changes with altitude. So dt, dh along an adiabat. And this is good because it's an exact differential. We can break it up into parts. It's dt over p and dp over dh. Right? These are the two parts we've calculated so far, basically dt dp from the adiabat and dp dh from our non-uniform density. All right? So we had dp dh from last lecture, 9.2 was minus mpg over rt. So that's good. Our dt dp, we're going to be able to calculate from our adiabat, right? So let's start with t to the gamma, p to the 1 minus gamma equals a constant. So I'm going to rearrange so that I have the t's on the one side and the p's on another. Right? So I'm going to call this t equals some constant. Don't care what that constant really is. P to the 1 minus gamma over gamma. Let me write that so that's slightly more clear. 1 minus gamma over gamma. So this is all in the, right? Okay. Since this, I can constantly redefine that A, so it doesn't matter. So dt dp is now going to be A times, so what I'm going to do is I'm going to take the derivative with respect to P, right? So I'm going to have to take this whole term and bring it down. All right, so this is going to be 1 minus gamma to the gamma, A, P to the 1 minus gamma over gamma. So this, let's 1 minus gamma over gamma is 1 over gamma minus 1. I'm missing a minus sign. Let me pause and take a look at where my minus sign is. Found my minus sign. It's all the way up here. So when I took this P to the other side, this should have been P to the 1 minus gamma over gamma, or A P to the gamma minus 1 over gamma, which is going to be the same thing as A P to the 1 minus 1 over gamma. Great. Haha. So when I took this down, I took the wrong thing down because I didn't have that minus sign. Okay, so this is 1 minus 1 over gamma. And you can see when I'm going to just subtract the 1, I'm just going to have minus 1 over gamma. Okay. Excellent. Now, I don't want to have this A in there, right? That's some arbitrary constant. So let's see if we can get rid of that A by rewriting this to get rid of that A, okay? So let's see if we can rewrite this in terms of A to the 1 minus gamma, okay? Okay, that what I mean is take T, T, A, P, T, A, P, 1 minus 1 over gamma, and rewrite that. Excuse me. No one's here for me to sneeze on them. Excuse me. T to the A, sorry, TA, P, P to the minus 1 over gamma. Right? Or, so I just separated that. So I can rewrite this as this is losing my mind. T, got caught sneezing and stopped thinking. T equals A P to the 1 minus gamma. So I just brought that out. Okay, so now I'm going to rewrite the A to P to the minus gamma as A P minus 1 over gamma equals T over P. Excellent. So dt dp is going to equal 1 minus 1 over gamma T over P. Very good. Very, very good. Now, let me take a look. Oh, I see. Yep. So now all we're going to do is combine them, right? So dt dh is going to be 1 minus 1 over gamma T over P times dp dh right? So you can basically think of dp as 1, right? So when we did this step, we just multiplied by 1. So we calculate dT/dP, and now that's that. We calculate dP/dH here, so let's put that in. So this is times minus mPg over RT. Very cool, because you can see actually this T cancels that T, and this B cancels that P. So dT/dH is going to be minus 1 over gamma mg over r. Getting quite simple. That's nice. So for air, so let's just do this for air. Gamma was 7/5, remember? So dT/dH, dT/dH for air. Let's just make sure I tell you that it's adiabatic, right? Is minus 1 over 5/7 times 0.029 times 9.81 over 8.314. So this is minus 0.0098. What are my units? It's Kelvin per meter. So you should go through your units and make sure that those make sense, and that's what you got. Or another way to say this is you're going to drop, so delta T of approximately 1 Kelvin for every delta H of 102 meters. Now, in actuality, the decrease is slightly smaller, right? So reality is slightly less. And that's because there is some heat exchange with the environment. So that's just going to keep it from dropping in temperature quite so fast. So that's very cool. That's called the adiabatic lapse rate, and it's quite a fun thing to think about. All right. So when you're going on a mountain climb, you've got your altimeter on your iPhone. I don't know. Your phone has Firefox. You can have an altimeter. You can actually calculate that the temperature should drop by 1 degree for about every 100 meters. Go on a hike and tell me if this is correct. Okay, so we're going to stop lecture 9 here. We're going to work out a very extensive example of work and heat in closed loops in class. And then we'll go on to lecture 10. So I'm going to take and do a little bit of lecture 10 today. Okay, see you next time.